Hi, this is part 2 of the Simple Machines section. In this, we're going to explore a couple of simple machines and learn how to calculate VR based on their geometry. Okay, so we have just finished part 1, so we learned a couple of things. First of all, what we learned were a couple of terms. So we had MA, which was a ratio of forces, and larger compared to the small, so force of my load compared to my force of my effort. I also had VR, which was a measure of the machine's geometry. So it was the distance that the effort moved compared to the distance that the load moved. And then I had an efficiency term, which was the measure of the mechanical advantage compared to VR, which is the geometry or the best possible effectiveness of that machine. Okay, so let's look at this machine first. So this is a wheel and axle. In the textbook, you're provided with an image. Some students have a hard time kind of understanding what they're really looking at. So I'll just sketch out what it really is. What you have is a cylinder that would be, I guess, attached to a larger cylinder. And on that cylinder, we might have some string that's wrapped around and would lead to the effort, so that's where I would pull. As well, what we might have is some more string that's wrapped around this smaller cylinder, and that would lead to your load. So pulling on the effort means I can amplify the force and lift a heavier load. This whole thing would rotate about a central axle. Okay, so we have our machine, and we have to kind of figure out how would we find VR? And VR is always going to be a measure of the geometry. So we need to figure out how far would my load move relative to my effort. Okay. And a lot of these machines that operate in a circle, often what we want to do is consider that this whole machine is going to rotate. So if I was to take my effort and do an entire revolution, I might want to know how far did my effort move, or how much string was unwound off of that circle. And doing so, how far would my load have moved? Well, the good news about the geometry of this machine is it's fairly straightforward. What I have are two circles. And if we wanted to find the circumference of a circle, so the circumference is going to be equal to pi d. So if I want to find the VR for my wheel axle, my VR is going to be the ratio of distances. So the distance of my load, the distance of my effort compared to the distance of my load. The distance that the effort would go, you can see on a diagram I've used, or there's a capital D and a small d. So I'm just careful because I've used d as sort of my distance, but in this I'm going to use it as diameter. So what I would have is my large diameter times pi divided by my small diameter times pi. The pi on the top and the bottom are going to cancel each other out. And so what I have for VR for a wheel and axle is a ratio of d upon d. also, if you're given a radius, it would be a measure of the large radius compared to the small radius. Okay, so we have two ratios. In real terms, we often talk about things in diameters. If we were to measure this machine, we would measure its diameter. It would be difficult for us to measure its radius. So diameter ratio is how we come up with our VR, and that's strictly a measure of the geometry of the machine. Okay, so we have an example question on wheel and axles. So we have a load that's being lifted with a wheel and axle system. Machine efficiency is 92%. In a large wheel and axle system, the wheel radius is 0.9 meters and the axle radius is 12 centimeters. How much actual effort must be applied to the machine to lift the load? Okay, so we'll start out with the same sort of process that we've gone through. Let's make note of what we know out of the problem. Let's ensure that all of our units are consistent, and then we'll start diving into the equations. Okay, so first of all, I'm just going to make a little list. Force of the effort, force of the load. I'm going to need to know, or I know from the problem, I'll know my efficiency. In this one, sometimes I've used distance one way or the other. They've given me some information on the radius. So I'm going to use large R, I'm going to use small r, and I think that's kind of what I need to know to get started here. So I know that my load is 850 kilonewtons. Machine efficiency of 92%. So 92%. Always remember we want that as a decimal, so divide the 92 by 100 and I would get 0.92. Okay, so I've used capital R to signify the largest radius, 0.9 meters. And the axle radius is my smaller radius, so 12 centimeters, so is equal to 12 centimeters. I want to make sure that my units are consistent. Meters and centimeters are not, so I'm going to multiply by 1 meter per 100 centimeters, and I'm going to get 0.12 meters. I also could have switched my large radius to centimeters. Doesn't really matter what unit I pick as long as they're consistent in this problem. Okay, so from there what we're going to do is we're going to figure out our VR. So for a wheel and axle, VR is going to be large radius compared to the small radius. 0.9 meters compared to 0.12 meters. Double check, make sure my units are consistent and will cancel themselves out. And when they do, I'm going to be left with VR of 7.5. Okay. I have efficiency, and efficiency is going to be equal to MA over VR. So if I'm solving for MA, which is going to talk about forces for me, so when I have MA is going to be equal to efficiency times my VR is going to be equal to 0.92 times my VR, which is 7.5, and that gives me an MA of 6.9. Okay, final step is to use MA to figure out my forces. So MA is equal to my force of my load compared to the force of my effort. I want to solve for the effort. All right, so I want to solve for the effort. So rearranging this, what I'm going to get to is an equation that says force of effort is equal to force of load divided by MA. So it's equal to 850 kilonewtons divided by 6.9 gives me 123.2 kilonewtons. Watch out down there. Didn't specify a unit in my problem, so that's okay. Looks like that would be my final answer. One thing that's interesting is you may get questions about levers in your third class exam, even though sometimes they're not necessarily listed out in your textbook or as part of the content. But just like to outline to you that in general, a lever is the same as a wheel and axle. Okay, so if you had a wheel and axle and it has some pivot point, essentially it acts the exact same as if we had a lever that had some fulcrum. So when we measure our lever, what we have is a ratio of the lengths of the free end compared to the other end of the lever. And we do the same approach with our wheel and axle. And in fact, if you did a full revolution with that lever, you would find that you have exactly the same answer. So for a lever, if we had a small length and a large length, sometimes we consider that. VR for the lever is going to be the ratio of your large side compared to your small side. And it's the exact same approach and the exact same thought process as we would go through to find the VR for a wheel and axle. Okay, so if you're faced with a lever question, consider that it's basically the same analysis as a wheel and axle. Okay, so the next simple machine that we need to be able to figure out VR for is a system of pulleys. Okay, so we have a standard arrangement of pulleys where they're going to go one continuous string up, down, up, down, up, down through a series of pulleys that would be held together in what would be called a block. Okay, so bottom block, top block, load block, but basically a collection of pulleys. Okay, so let's go through the approach for how we're going to figure out a pulley. Okay, so I'm going to draw out a couple of examples here. One, we've got a couple of ceilings here. Okay, so there's our fixed ceiling, and we're going to try and lift a 1,000 Newton load. Okay, and so I have 4 pulleys that I can arrange. So we'll say 2 in the top block, 2 in the bottom block. And really, if I draw it out, what that could look like is I've got 2 pulleys down on the bottom and 2 on the top. Okay, and so I have one way that I could arrange that, which is that I could start my rope and tie it to the ceiling, and I could work my way up and down, up and down, and up and down. And say these guys get connected to the loads. Okay. I also have an alternate method that I could attach that, and that would be to start, instead of the load attached to the ceiling, it starts on the block itself, or on the load itself, and I've got 4 different pulleys, and my rope winds through those series of pulleys and then makes its way up. Okay, so I have 2 different arrangements of my pulleys. let's see if we can figure out how to analyze these and understand how we could figure out a VR for each of those systems. Okay, so here's the approach I'm going to take. What I'm going to do is I'm going to essentially cut through both of these systems. Okay, and what I know is that if I was to make a imaginary cut through there, these things are still being held up, and they're being held up by the tension in those lines. And if I can figure out the tension in the lines, and it's the same all the way through my system, then what I can do is try to figure out, how much tension is in each of those lines. Okay, so if I kind of made my cut through here, and let's make a cut through here, and let's make even a bigger cut so we kind of ignore the top half of this, and let's figure out how many forces are holding up. Well, in this case, I've got 1, 2, 3, and 4 lines that are holding up the object. So if I was to find out what the tension was, the tension is going to be the 1,000 newtons divided by 4. So in this case, 250 newtons. Okay. I have a slightly different arrangement, okay, over on this other side. So where I cut it, now I have the 4 ropes that are at the pulley, okay, but I've also gained another line. So if I was to find my tension here, my tension is going to be the same 1,000 newtons that has to be shared by 5 strings, or 5 pieces of tension. And so I have 200 newtons as my tension. Okay, so the arrangement matters. So when I go to find VR, I have cases where I do a better job potentially with my forces than other arrangements. So we have a case where if we have an upwards pull, okay, so over here the arrangement ended up that my pull was in the upwards direction, which tends to help. So when I'm pulling upwards, I'm also lifting some of the load. And when I have an upwards pull, my VR is equal to the number of pulleys plus 1. So in this case that I provided you, we had a factor of 5, which was indicating how much VR we had. And we had 4 pulleys plus 1, which got us to our 5. If we're pulling in the downwards direction, we have a situation where my downwards pull does not help me lift my load. It's only changing the direction of my pull to help me downwards. And so if I have a downwards pull, so my downwards pull, VR, is equal to the number of pulleys. Now, physically, it may be easier for us to pull downwards because we're using our own weight to help us provide that tension than for us to be pulling upwards. So we have some benefit to pulling down. However, from a machine design, it's better to be pulling upwards against that load because we have a higher VR value. So if we were to take a look at this example of a pulley system, let's see if we can figure out what our VR is. Okay, so a couple of approaches. One, what we can do is, first of all, count the number of pulleys. All right, so if we were to count the number of pulleys, 1, 2, 3, 4, and 5. So we know that our VR is either going to be 5 or one more, 6. So then we just have to figure out the arrangement. One, we can figure out that our pull is ultimately in the downwards direction. And pulling downwards does not help us because it's going in the opposite direction than would be helpful. So if we want it to pull upwards, that would be more helpful for us to lift that load. So the downwards effort is the lower VR approach. So what that means is that in this case, my VR is going to be 5 in the downward direction. The other approach that you could take is you could look at the individual strings that are supporting the load under tension. So if we looked at what was holding up the load, we had 1, 2, 3, 4, and 5 sections of string that are directly connected to that load. And so the 5 of those guys would be equal to our VR. Okay, so sometimes it makes sense to draw out a little diagram. Sometimes it can be helpful for you. Or else if you remember the up and down, that's another easier approach than drawing. Okay, so let's take a look at this example. I have a fixed block and a movable block. Okay, so the block, again, the terminology. Wondering what my VR might be. Okay, so a couple of approaches. One, I'm going to count my pulleys. So I have 2 in the bottom. So 1, 2, 2 at the top. So 3, 4. So my VR is either going to be 4 or 5, depending on the arrangement. However, the upwards effort helps to lift the load as well. So I gain an extra unit on my VR. So my VR would be 4 plus 1 equal to 5. The other thing we could do is we could also look at the load block itself and count up how many places is it being supported. So 1, 2, 3, 4, and 5 supports off of there means that I would have a VR equal to 5. Okay, so either approach will get you the same answer, whatever one you're more comfortable with. Draw out a little sketch or use a diagram if it's provided, or else understand up or down that convention. Okay, so let's do a couple of example problems on block and tackle pulley systems. Okay, so example 10, we have a block and tackle system, 3 pulleys in each block, and the effort is applied downwards. Okay, so a couple of approaches for figuring out VR first. One, what you could do is draw a little diagram. You got your roof, we got 3 pulleys, we've got 3 pulleys. The effort is applied downwards, which means we end up going like that. And so if I work my way through my pulleys, it turns out I would connect to the roof. And what you could do would be to count up how many of these ropes are supporting my load directly, and it turns out that that is 6. Okay. The other thing we could do is just by memory, we could remember that a downwards pull is equal to the number of pulleys, and we do not add an extra one because the downwards pull doesn't help us lift that load. So in this case, my VR would be 6. Okay, so I'll just make note of some of the stuff I know. VR is going to be 6 in this case. The force of my load, I'm going to need force of an effort, and I'm trying to find an efficiency. Okay, so find the efficiency given an effort of 300 newtons, required to lift a mass of 160 kilograms. Okay, so got to be careful here. What I've been given is a mass of 160 kilograms. In order to turn that into a force, a weight, the weight is going to be equal to mass times gravity. So 160 kilograms times 9.81 meters per second squared is going to give me a value of 1,569.6 newtons. And that would be my force of my load, 1,569.6 newtons. So in order to find efficiency, I need to know VR and I need to know MA. So my mechanical advantage is a ratio of forces. And it's the larger force, the load, compared to the effort. And that is 1,569.6 newtons divided by 300 newtons. Double check, make sure my units are the same, and they are, so my units will cancel themselves out. So 1,569.6 divided by 300 gives me an MA equal to 5.232. Okay, a couple things just before I get any further. One thing we need to make sure we know. VR is the best possible use of this machine or arrangement of this machine. So MA, if there's any inefficiencies, is going to be lower than my VR. Okay, so I'm happy that I have 5.2 as my answer because it's less than the 6 that I have for VR. So right away, I'm fairly confident with that number. If I had a number that was above 6, I would know that I've made a mistake somewhere. Okay? If I have a value that's below 1 or close to 1 or significantly different than the 6, I might second guess my value and wonder if I've done a good job. But looking at that, I think the numbers make sense to me moving forward. Okay, my efficiency is a measure of the MA compared to VR. And my MA 5.232 divided by 6. 5.232 divided by 6 gives me 0.872. That's always as a decimal. If I multiply that by 100, I could get it as a percentage, 87.2%. Okay, we have an example number 12. And example number 12 is a little more complicated. However, it does have an error in it. The number of pulleys it's specified is not the correct arrangement. So it should be 3 pulleys in the load block and 4 pulleys in the support block if your textbook version has that incorrect. So 4 pulleys and 3 pulleys. Okay. The other thing that's different about this question is that instead of it being a vertical load, it's a horizontal load. So we'll have to make sure we understand some of the arrangement details when we're figuring out our VR, because it's no longer an up or down pull, but we have to make sure we have the right VR for this. So block and tackle with a certain number of pulleys in the load or support block has an efficiency of 90%. Effort is applied towards the load block. Okay, so we'll make sense of that. The load consists of an exchanger bundle being pulled horizontally from the exchanger shell. So what we have is we have some object that we are trying to pull horizontally and using a block and tackle system. And I guess it's going to some fixed object that's pretty strong. When we talk about the load block, that's going to be closest to what we would consider to be our load. Okay, so we're going to have 3 pulleys in the load block. 1, 2, 3. And I guess that means we have 4 pulleys in the support block or against the wall. Okay. The effort is applied towards the load block. Okay, so we're going to start out with a pull in that direction, and I'm just going to wind my way through my series of pulleys, and I guess that guy's going to tie into the load. Okay, so if I'm figuring out VR, a couple of approaches, right? We can either count up all of the loads that are, or the lines that are supporting the load directly. So 1, 2, 3, 4, 5, 6, 7. Okay, so that approach is going to tell me VR is 7. The other approach that I can do is an upwards or downwards pull. But it becomes a little goofy because I don't have upwards or downwards pull. So what we want to do is, I guess, just assume we're going to rotate this whole thing 90 degrees, which would mean that my load would be pulling in that direction. Okay, if it was gravity, that's the way the load would be pulling, which means really what I have is a downwards pull. And if I use my same rules for a downwards pull, or a pull that's going in the direction towards the load, my VR in this case would be 7. Okay, so we've got VR organized, so now the rest of it should be okay. What we have would be some forces, force for an effort, we have a force for a load, we have an efficiency, we have a VR value. Fill in what I know. Okay, so I do know that I have a total force required to overcome the mass of the friction is 850, which is essentially my load, 850 kilonewtons. I have an efficiency of 90%. I want to express that as a decimal, so 0.90. And then I have VR, which we calculated as 7. Okay, so efficiency is going to be equal to MA over VR. Or if I want to find my MA, it's going to be equal to VR times my efficiency. And that's going to be equal to 7 times 0.9, and that's going to be equal to 6.3. My MA is also equal to my ratio of forces, my force of my load, which is the larger value, compared to the force of the effort. If I'm going to solve for force of effort, my force of effort is going to be equal to my force of my load divided by MA, 850 kilonewtons divided by 6.3. $134.9 kilonewtons. Okay, we have a third and final machine to be able to calculate VR, and that's a screw jack. Okay, and so a screw jack is going to be used to lift a load using a threaded rod. So we turn a nut, and as the nut moves up, it will be able to lift a load. Okay, so how we calculate VR for a screw jack is going to be that we have to look at how does this thing change, so relative to our effort compared to our load. Okay, so VR is always the distance that our effort moves compared to the distance that our load moves. Okay, and so if we were to figure out our distances, what we would consider is what would happen in one revolution. So if we take our handle and we do a complete revolution, well, how far did it go? Well, it created a circle, and that circle would have a circumference of pi d. However, we usually don't have a d. What we have is some length of handle, which is in fact a radius. So pi times 2 radiuses would be the circumference. And that would equal the distance that our effort moves. So then the question then would be, well, how far is the load going to go in one revolution of that handle? Okay, and it's going to be dictated by the thread. Okay, in this diagram, what they've shown is a term, the pitch. Okay, and the pitch is often what we're going to use to dictate the distance that screw jack moves up, but it's not always the case. Okay, so we have VR, which is equal to the distance that our effort moves. So we may call it like 2 pi L. So L, if we use the L value that's shown in the diagram, or else a radius. So, but I think the length of your handle would be the L value that we use, compared to the distance that the load moves. And we have a pitch. Okay, the pitch, if we look at what pitch is the distance between the top of 2 threads. Okay, so if we have a thread and we follow it along, when we move through a full revolution, that thread is going to indicate how far up that threaded rod did we travel in one revolution. So in what's known as a single threaded rod, or a single threaded screw pitch, then we're going to have pitch as the height in one revolution. And single threaded rods make up 95%, 99% of all screws. So they're all, for the most part, going to be single threaded screws. In screw jacks, often what we have are double threads. And if we look at what happens that's different about a double thread, is that if I followed through one of these pitches, it kind of comes through like this, and then when it turns around through the back, it connects through over here. So what I have is not one thread that keeps continuously traveling, is I have 2 threads that keep traveling. Okay. So I have those in screw jacks because they typically allow me to screw something and have it travel faster, so up and down faster. So there's some advantages to having a double threaded rod, and in that the object moves up and down the threads faster. The difference in terms of VR is that now I'm not using just pitch, because pitch is defined as the distance between the top of two adjacent threads. In this case, what I have is a term which is lead. Okay, so my lead is really equal to the pitch times the number of threads that I have on the object. Okay. And really, when I come up here to go back to looking at my VR is really 2 pi L over the lead. Okay, so that's not quite right. And the other way maybe that we look at it is it's 2 pi L upon the number of threads times the pitch. Okay, so in your questions in your third class level, you'll certainly have the variable of how many threads is that rod. Is it a single threaded rod? Is it a double threaded rod? And you'll have to make sure that you understand how that's going to influence your VR. Okay, so we're going to look at a example 13. A screw jack has a single start thread and a pitch of 12 millimeters. The handle is 500 millimeters long and an effort of 250 newtons is applied. If the efficiency of the jack is 50%, what load can be lifted? Okay, so we'll start with figuring out our VR. So VR is going to be equal to 2 pi L, the circumference of the circle that's described by my effort as I rotate my wrench or my turning handle through a full revolution. And then that's upon the lead. And my lead is equal to my number of threads times the pitch. Okay. Given in my question, I have the number of threads, which is a single start thread, so that means one thread, times the pitch, which is 12 millimeters, and my lead is equal to 12 millimeters. Okay, so VR is going to be equal to 2 times pi times 500 millimeters upon the lead of 12 millimeters. Checking to make sure I'm consistent with my units, so millimeters is going to cancel itself out. So 2 times pi times 500 divided by 12 gives me a value of 261.8 as my VR. Compare that number to previous VRs. We had pulleys with VRs of 5 or 6 or 8. This is significantly more effective machine. So in the hundreds for a screw jack. My efficiency is equal to 50%, 0.50. And efficiency is also equal to MA over VR, which means that my MA is going to be equal to VR times 0.50 equal to my 261.8 times 0.50. 130.9 is the effective mechanical advantage. MA is equal to the force of my load compared to the force of my effort. and it's equal, or if I rearrange to find my force of my load, is going to be equal to MA times the force of my effort, 130.9 times 250 newtons. So 32725 newtons.